Welcome everybody to another calcaholic video. Today we're looking at logarithms and exponentials for both the natural and general cases. So before we even look at any logarithmic or exponential functions, I want us to know what non-elementary integrals are. So non-elementary integrals are integrals that can't be expressed in terms of basic algebraic operations. So for example, summation or multiplication, division. You can't express the integral with those type of operations. So what do? Well, it's very common in mathematics to assign a new function for the integral. So for example, the integral of cosine x over x dx, we call the cosine integral function with input x and obviously the integral constant. So what about for this integral here, the integral of 1 over x dx? Can you integrate it? Can you express it in terms of basic algebraic operations? The answer is no. You cannot use the reverse power rule here, simply because the condition for the reverse power rule is n cannot equal -1, and in this case n is equal -1. So what do we do? Well, mathematicians will assign this function ln x to this integral, and that is the integral definition. So theorem: the derivative of the natural logarithm is equal to 1 over x, and I'll be referring to the natural logarithm as ln x for the rest of this video. So recall, ln x is equal to the integral from 1 to x of 1 over t dt. This implies that taking the derivative of both sides will give us 1 over x. And this is simply just due to the fundamental theorem of calculus. The differentiation operator cancels out with the integral operator, and we just have to plug in the bounds and subtract. So plug in the bounds here, we get 1 over x. Plug in the bounds here, well, this is constant, so when you differentiate a constant, it goes to 0. And therefore, we can conclude that the derivative of ln x is equal to 1 over x. Theorem: ln of 1 is equal to 0. So recall again that ln of x is equal to the integral from 1 to x. So this implies if we put an input of 1 for x, we get ln of 1 is equal to the integral from 1 to 1. No matter what the function is, if our two bounds here are the same, then we're integrating under a point. And if we integrate under a point, we're just going to have a one-dimensional line under our curve, and one-dimensional shapes don't have area. It's just a line. So the area under that curve is going to be 0. Therefore, we can conclude ln 1 is equal to 0. Alright, now the natural logarithm laws. Note the conditions q greater than 0 and p greater than 0, and r is a rational number. So point 1, ln of p times q is equal to ln of p plus ln of q. Point 2, ln of p over q is equal to ln of p minus ln of q. And point 3, ln of p to the rth power is equal to r times ln of p. Alright, starting with the proof of our first point, if you take the derivative of ln of p times x with respect to x, using chain rule, we'll get the derivative of the outer function times the derivative of the inner function. So it's 1 over px, because input is px here, times the derivative of the inner function, where inner function is px. So p is constant here, x is variable, and we're differentiating with respect to the variable x. So we get p over px. These p's cancel out and we get 1 over x. We also know that the derivative from the first theorem is equal to ln x. So this implies that the derivative of ln of p times x is equal to the derivative of ln x. Okay, noting that, this implies that integrating both sides should also hold the equality. And this is true. Integrating both sides will cancel the differentiation operator and leave us with ln of p times x is equal to ln x plus c. Okay, well, the issue is we have a plus c, a constant of integration. So how do we determine it? Well, let's evaluate this at x equals 1, and this will give us that ln of p is equal to c. So let's make the substitution for c, and we'll get ln of p times x is equal to ln x plus ln p. Now let's evaluate x at q, and we'll get that ln of p times q is equal to ln of p plus ln q. Right. Now I'm going to jump actually from proof 1 to proof 3, and there's a reason for this, because proof 3 is needed for proof 2. So we're going to start with the proof of 3, or point 3. The derivative of ln x with input x to the rth power gives us 1 over x to the r, because of chain rule, times the derivative of the inner function x to the r. So this is just the power rule. Okay, well, we can rewrite x 1 over x to the r as x to the negative r. And using the exponent laws that we know, we can, since these are same base, we can add their exponents. So we have an r plus a negative r. These r's will cancel out, leaving us just with an x to the negative 1 power. And this is equal to r over x. Okay, now let's take the derivative of r times ln x. R is constant, so we can pull it out of the differential operator and take the derivative of ln x. The derivative of ln x, as per theorem 1, is equal to r over x. Okay, well, this implies that both derivatives are equal, so then we can also integrate both sides and the equality holds. Okay, well, this implies that ln of x to the rth power is equal to r times ln x plus c. Again, plus c is an issue. Let's evaluate this quality at x equals 1. And this will give us that c equals 0, so there's no problems with the c. Therefore, we can conclude that ln of x to the rth power is equal to r times ln x. Alright, now proof 2, by proof 1 and proof 3. So ln of p over q is equal to ln of p times 1 over q. Right, we're just separating these. Okay, and by proof 1, we can separate them by summation. Right, the first logarithmic law is by proof 1. Now by proof 3, let's first rewrite 1 over q as q to the negative 1 power, and we can bring the negative 1 down from the exponent. Therefore, ln of p over q is equal to ln of p minus q. So we did proof 2 by proof 1 and proof 3. Alright, next two theorems. The limit as x approaches infinity for ln x is equal to infinity, and the limit as x approaches 0 from the right hand side of ln x is equal to negative infinity. Alright, proof of A. The derivative of ln x is equal to 1 over x, and because 1 over x is always greater than 0, and x is always greater than 0, because that's the domain of ln x, then ln x is an increasing function for all x greater than 0, or you could say for all of the natural logarithms domain, being 0 to infinity. Therefore, as x increases, ln x increases, implying that the limit as x approaches infinity of ln x diverges, and more specifically, it diverges towards infinity. Now, proof of B. The limit as x approaches 0 from the right hand side, denoted by this positive, of ln x is equal to negative infinity. Let's t equal 1 over x, or x equals 1 over t, right? These are the same thing. So let's make those substitutions for x whenever t is equal to 1 over x, and we're trying to get x really close to 0, t will be approaching infinity. So we can rewrite this limit as t approaches infinity instead of 0. And then making the substitution here for x, it's 1 over t, so we write ln of 1 over t. We can rewrite this limit by putting t to the negative 1 power and pulling the negative 1 down by proof 3. And this will give us negative 1 times the limit as t approaches infinity for ln of t. And now by proof A, we know that this limit approaches infinity. So this is basically positive infinity times negative 1, which of course is negative infinity. Alright, now the natural exponential function. Recall that the range of the natural logarithm is negative infinity to infinity. Thus, there exists a y for all x such that ln y equals x. Because the derivative of ln x equals 1 over x, then ln x increases if and only if x is greater than 0. And right, that's because if x is less than 0, then x is technically decreasing in this case because the first derivative will be negative. So we're assuming that ln x increases if and only if x is greater than 0. And now since ln x increases, then ln x is injective, because for all functions that are purely increasing, they are one-to-one functions, so it is injective. Now we can conclude that since ln x is injective, there exists a unique inverse function such that the inverse function of ln x equals x. Alright, so page 2. Let ln y equal x, which would imply that the inverse of x would equal y. Now let's denote the inverse of f as exp, or exponential. This would imply that ln y is equal to x. You can write it in terms of the inverse function. The exponential of x is equal to y, because we've defined the exponential in a way where it is the inverse of ln. Now let's denote the exponential of x as e to the power of x. So the input is in the exponent rather than just like a function input. Therefore, e to the power of x is equal to y if and only if ln y is equal to x. So, what are some properties of the natural exponential? Well, let's recall that the domain of ln was 0 to infinity. And since we've defined the natural exponential to be the inverse, that means the range of the exponential must be 0 to infinity. Again, point B here, the range of ln is negative infinity to infinity. Therefore, we can assume that the domain of the exponential is negative infinity to infinity. Of course, this is the property of inverse functions. This comes from reflecting our curve across the line y equals x, which in turn swaps x and y, which in turn swaps the domain and range. So the inverse function, going from the regular function to the inverse function, just swaps the domain and range. So because ln with input e to the x equals x, therefore e to the x is greater than 0 for all x, right? Because the natural logarithm is not defined for values of 0 and less. So e to the x has to be greater than 0 for all x. Alright, laws of natural exponentials. If p is a real number and q is a real number and r is a rational number, then the three following points are true. Point 1. E to the p times e to the q is equal to e to the p plus q. Point 2 reads e to the p divided by e to the q is equal to e to the p minus q. Point 3 reads e to the p all raised to the power of r is equal to e to the p times r. Right? These are the exponential laws that we see in, like, I guess, Algebra 2, Integrated 3, or Pre-Calc. The proof of point 1. Alright, let's start off with the natural logarithm with input e to the p times e to the q. We can separate these into two terms by point 1 for natural logarithm laws. This is equal to ln of e to the p plus ln e to the q. And this implies that ln e to the p times e to the q is equal to p plus q, right? Because the natural logarithm, in this case over here, is canceling out with the e, and this is because there are inverse functions. So if you go back to the definition, we put ln of e of x is supposed to give back x because they're inverse functions. So this should give back a p, and this should give back a q, which it does. It gives p plus q. Okay, so p plus q is equal to ln of e to the power of p plus q, right? Because we're taking ln e, these cancel out, so this is basically multiplying by 1, I guess. This implies that ln of e to the power of p times e to the power of q is equal to ln e with input e to the p plus q. Now, since ln is injective, so that means that every y value is unique for every x value. If this output value of ln is equal to this output value of ln, therefore their inputs must be equal, right? Because this is an injective one-to-one function. So if somehow we're getting the same y value, that must mean that we're at the same x coordinate. So that means e to the p times e to the q is equal to e to the p plus q. Alright, proof of point 2. So basically the same thing. We have ln with input e to the p over e to the q is equal to ln e to the p minus ln e to the q, again by the first logarithmic law. This implies that ln of e to the p over e to the q is equal to p minus q. Again, this ln and this e are canceling out because they're inverse functions. That's how we have defined the natural exponential. Alright, this implies that p minus q is equal to ln of e to the power p minus q. Again, because these are inverse functions, so this did not change the equality. This implies that ln of, with input e to the p over e to the q, is equal to ln of e p minus q. Again, since ln is injective, these values of ln are equal to each other, which means their inputs must be equal to each other because ln is a one-to-one continuous function. Therefore, e to the p over e to the q is equal to e to the p minus q. Alright, proof of 3. Again, we're going to start with the natural logarithm with input e to the p all raised to the power r. This is equal to r times ln e to the p. This is that natural logarithm law where you can bring the exponent and make it a product. So we have r times ln e to the p. Well, we know these are inverses again, so they cancel and just leave us with the exponent here, p. So we get r times p. This implies that r times p is equal to ln e raised to the r times p. Again, this doesn't change the inequality because these are inverses. They will cancel out and we'll end up multiplying by 1. Alright, so this implies that ln with input e to the p all raised to the power of r is equal to ln e to the power of r times p. Again, since ln is injective, this means these values of ln are equal, and because it's a injective one-to-one continuous function, if y values are equal, their x coordinate must be the same, so we can conclude that e to the p to the power of r is equal to e to the p times r. Alright, theorem. The derivative of e to the x is equal to e to the x, and here's the proof on the same page. We can denote x as ln e to the power of x, right? Because this is inverses, they cancel out, we're multiplying by 1. So we can differentiate the left and right hand side with respect to x, and we'll get 1 over e to the x times the derivative of e to the x. We'll multiply e to the x to the other side, or on both sides of the equation, and we'll get that the derivative of e to the x is equal to e to the x. And we got this on the left hand side, just for clarification, because we're differentiating the natural logarithm with input e to the x. So it's 1 over the input e to the x times the derivative of the input. This is just chain rule. Alright. Now general exponential functions. The general exponential definition. So for all a greater than 0 and for x that is a real number, then we have the following equation. A to the power of x can be rewritten as e to the power of x ln a. And why this is true? Well, if we take this x, put it back in the exponent since it is a factor, we have e to the ln a to the x. The ln and the e cancel out because they're inverses, and we're just left with a to the x. So we know this this equality holds true. So here are the 3 most common laws of exponents. I didn't feel the need to include the quotient version of this 0.3, and I didn't feel the need to include the quotient version of 0.1 either, because of course right here a to the negative v, and this is just minus v, so it is the same thing. Anyways, proof of 0.1, a to the power of u plus v is equal to e to the power of u plus v all times ln a. Again, this holds true because you can throw u plus v into the exponent of ln a, and the ln and the e will cancel out, so we know that the equality holds true. This implies that e to the power of u plus v times ln a is equal to e to the u times ln a plus v times ln a. Here we just distributed the ln a into the v and into the u. So this implies that e to the u times ln a times e to the v times ln a is equal to a to the power of u times a to the power of v. And we did this by exponent loss. We separated the addition here by multiplying same base. So that's what we did over here. This is equal to a to the u times a to the v. Therefore, a to the power of u plus v is equal to a to the power of u times a to the power of v. Alright. Now the proof of 2. Here we're saying that a to the power of u all raised to the power of v is equal to e to the power of u times ln a all to the power of v. Okay, we're going to multiply the v into the exponent here, and we'll have e to the power of u times v times ln a is equal to e to the ln a all to the power of u times v. Here the ln and e will cancel out, leaving us with just a to the power of u times v. Therefore, a to the power of u all to the power of v is equal to a to the power of u times v. Alright, proof 3. So here we're saying that a to the b all raised to the power of u is equal to e to the u ln a times b, right? This is the same kind of thought process with all the other proofs as well. So this is equal to ln of a plus ln of b, right, by the first logarithmic rule that we proved. So then we can distribute the u to each term here of ln, and then bring that u into the exponent. So then these e to the ln's will cancel, leaving us with a to the u times b to the u. Therefore, we can conclude that a times b all raised to the power of u is equal to a to the power of u times b to the power of u. Alright, now here is a theorem that it proves the power rule. So we're saying that the derivative of x to the power of n is equal to n times x to the power of n minus 1. And here's the proof for this theorem. The derivative of x to the power of n is equal to the derivative of e to the n times ln x. Of course, just like all the other proofs, you can bring ln or the n back into the exponent of x and then cancel the ln and e because they're inverse functions. So we know this equality holds true. This implies that e to the n times ln x times n over x is equal to x to the power of n times n over x. Again, this is just the derivative, so let me kind of go over that a little bit. The derivative of e to the power of some function is e to the power of some function times the derivative of the function. So again, we have e to the n ln x, and then times the derivative of the inner function here, which is n ln x. N is a constant, so we take it out the differential operator. Ln x, we know its derivative is 1 over x, so then we're multiplying by n times 1 over x. That's basically what that is. And this is equal to n times x to the power of n minus 1. This is because we're dividing by x here, so we can just subtract 1 because that's what its exponent is. Therefore, the derivative of x to the power of n is equal to n times x to the power of n minus 1. And this is just the power rule. Alright, theorem. The derivative of base a to the power of x is equal to a to the power of x times ln with base a. Proof on the same page. The derivative of a to the x is equal to the derivative of e to the x ln a. Again, you can bring x to the exponent of a and cancel out because they're inverse functions, giving you a to the x, so we know this equality holds true. This implies that e to the x ln a times ln a is equal to a to the x ln a. So again, like with the last theorem, if we're differentiating this over here, we keep e to the power function times the derivative of the function. So we have e to the x ln a times the derivative of the inner function. X is variable, ln a is constant, so x will turn into 1, so this is 1 times ln a, and that's what we have here, a to the x ln a. Therefore, we can conclude that the derivative of a to the x equals a to the x ln a. Alright, now the general logarithmic definition. For all a greater than 0 and x greater than 0, then the following is true. Y equals log sub a if and only if x equals a to the power of y. So here we're defining the general logarithmic function as the inverse of the general exponential function. Alright, theorems. For point 1, log sub a of x is equal to ln x over ln a. This is called the change of base formula. For anybody in pre-calc or calc AB, this is pretty useful. You're going to need to use this. For point 2, the derivative of log sub a of x is equal to 1 over x times ln a. And for point 3, the integral of log sub a of x dx is equal to 1 over ln a times x ln x minus x plus c. And I know I didn't go over the integral of the natural logarithm in this video because I feel like that's kind of out of the scope. For this video, I'm not going to go over integration by parts. That's outside of the scope of this video, so we're just going to assume that we know the integral of ln x for that definition. Alright, proof of y equals log sub a of x if and only if x equals a to the power of y. This implies that ln x equals y times ln a. And this we get just by taking the logarithm, the natural logarithm of both sides. For this right here, you take ln, so you get ln x, take ln, so you get y times ln a. This implies that y equals ln x over ln a. Therefore, we can conclude that log sub a of x equals ln x over ln a. Alright, proof of 2. By proof 1, log sub a of x equals ln x over ln a. This implies that the derivative of log sub a of x is equal to the derivative of ln x over ln a. Well, we know ln a is a constant in this case, where ln x is variable, and we're differentiating with x, with respect to x. So we can pull 1 over ln a out the differential operator, like you see over here, and just differentiate ln x. We've done the derivative of ln x many times. We know that it's 1 over x. So we can conclude that the derivative of log sub a of x is equal to 1 over x times ln a, where x ln a is in the denominator. Alright, now proof 3. By proof 1, log sub a of x equals ln x over ln a. The integral of log sub a of x dx is equal to the integral of ln x over ln a dx. Well, again, we know ln a is constant, so we can pull it out of the integral operator and just integrate ln x. We know that the integral of ln x is x ln x minus x using integration by parts. Therefore, we can conclude that the integral of log sub a of x dx is equal to 1 over ln a times x ln x minus x plus c, where c is some integral constant. And that is it for this video. If you haven't already, please subscribe. It would mean a lot. And if there are any videos, ideas, topics from your class that you want us to cover, please let us know in the comments. Yeah, leave a like if you have any questions, concerns, or anything of the sort. Leave a comment down below. Thank you all for watching. Have a great day.